Hi thinkers, welcome to the Artificial Intelligence playlist on ThinkX Academy. In this playlist we have already studied the hill climbing algorithm in which we have two variants. One is the simple hill climbing algorithm and the second variant is the steepest ascent, and we have studied about both of them. And in this tutorial we are going to choose a problem and then we are going to use steepest ascent hill climbing algorithm, and we will implement it in Python programming. So basically, if you have no idea about what is steepest ascent hill climbing algorithm, I will suggest you to watch the video on the playlist, and I will also give the link to that video in the I button here and also in the description. So let's start with the problem. Now we have now I'm going to pick a problem here, and the problem that I have picked is the traveling salesman problem, right? So it is a very popular problem, and we are going to solve this problem using the steepest ascent algorithm, and then we will also see the implementation part in Python in this video, right? So let's try to understand what this problem says. Now I have chosen a very simple subset of this problem so that it becomes easier for us to implement it, right? So let's suppose we have a salesman, right? So let's say there is a salesman here, and let's suppose there are some cities. I'm going to consider 4 cities at this point, right? So that we can so that the solution, the implementation will become easier. Now these 4 cities are connected with some routes, right? So let's say these 4 cities are connected with routes like this, and we have diagonal also, right? So these are also connected, and even these are also connected. Now let's suppose this is the city 0, this is the city 1, this city is 2, and this city is 3, and let's say the distance of the route from 0 to 3 is 300, and here we have 400, and let's say this is also 300, this is 400, and let's say these two diagonal routes are 500, right? So the distance of the routes is 300, 400 and 500. You can consider it as a rectangle here. So now what we have to do is, what the salesman has to do is, he has 2 things to do. First is to visit all the cities, right? Visit all the cities, and remember that you cannot leave any city. So the salesman have to visit all the city, and the second important constraint is that every city is visited only once, right? Visited only once, right? So this salesman have to visit all the cities in a fashion that he is not visiting a city twice, right? And what we want to do is, what the problem says is that we want to find out the shortest path, or you can say the shortest route, to satisfy these 2 constraints. So that is the problem. Now now we are going to solve this problem, right, which is to find the shortest route by using the steepest ascent hill climbing algorithm. I'm going to give you a very short summary of the steepest ascent hill climbing so that things will become more clear, and the concept you will be able to revise the concept also. So what we do is, initially at the first step in the algorithm, right? So here I'm going to, let's say we are going to write the algorithm, and this is the steepest ascent hill climbing algorithm, right? So I'm going to write here steepest ascent. This is the algorithm. In the first step, we actually if I try to draw a diagram here, we generate a solution, right, in our state space representation diagram, and then we find out all the neighbors that goes from this solution, and out of these neighbors we find out which one is the best neighbor, right? And we use the heuristic value for that. In our case, the heuristic value will be the route length, right? So from here we will find out some random neighbors some random solutions, and then we will find out which one is the best. So let's say this one is the best, so it means that we are going to disregard these two routes, and then these two solutions are disregarded, and then we will keep doing this, keep generating more and more solutions until and unless the goal state is reached, right? So let's say this one is the goal state, and after this one is the best neighbor, so we will disregard this solution, right? So we keep going on. The steepest ascent is this only. We are choosing the best neighbor using the heuristic value, right? So a very quick summary of steepest ascent. Now the first task in this algorithm is to generate a random solution, right? That is a very important part. Generate random solution, right? So what I'm going to do is, instead of writing the whole algorithm, we are going to follow it step by step, and at each and every step I'm going to write the equivalent Python code, right? So the first thing is we need to generate a random solution. You can see in the algorithm we have the first step, which is to generate a random solution and assign it as the current solution, right? That's the first step. You can watch that in the video of steepest ascent hill climbing algorithm. So how can we generate random solution in Python, right? So before that, if I try to implement in Python, the first thing we need to do is we have to represent this problem space in Python, right? So the way I'm going to do is I'm going to create an array. Let's say the array is TSP, which is the traveling salesman problem, and I'm going to assign it as a list of list, right? So basically a multi-dimensional array. So you can see from 0, let me write it here, we have 0, 1, 2 and 3. These are the cities, and here we have 0, 1, 2 and 3, right? So since this is a list of list, I'm going to assign something like this. This is the list, and inside this we are having another list. So from 0 to 0, you can see the length is 0. From 0 to 1, you can see the route length is 400, right? So I'm going to write 0 comma 400, and from 0 to 2 we have 500, and similarly from 0 to 3 I have 300, right? So this is going to be my first list, which represents the first row, and similarly we can use the same strategy to develop all the rows, and this is how we are going to generate the problem space, right? Now let's implement this in Python. First of all, I will open up my terminal, and basically I'm going to create a file here. Let's name our file as Python solution, or let's say TSP solution, right? TSP solution.py, since this is a Python file. And now we are inside of our Python file, and let me just zoom in so that you will be able to see things clearly. Let me move it here. Alright, so now we want to create a basic array, right? So first of all, let me just delete all this, right? So this is our Python file where we are going to write the whole program, and the first step is to create a TSP array, which is a list of list, right? So I'm going to just write it something like this, right? So this is a list of list, and here we have the first row, right? Inside the first row you can see that alright, so the first row says that from 0 to 0 we have the length as 0, right? And from 0 to 1 we have the length as 400, and from 0 to 2 we have the length 500, and from 0 to 3 we have length 300, right? So this is our first row, so separated by a comma, right? Now in the next line I'm going to create another row, and similarly we will have 4 rows, so I'm going to create 4 rows here, something like this. Right now we are going to focus on the city 1. So what is the distance from city 1 to 0? It's again 400, right? So it is 400. From 1 to 1 we have the distance as 0. From 1 to 2 the distance is 300, and similarly from 1 to 3 the distance is 500, right? So in this fashion we are going to create the whole array, the whole problem space. Now we are on 2. So what is the distance from 2 to 0? You can see the distance is 500, and then from 2 to 1 the distance is 300, 2 to 2 is 0, 2 to 3 is 400, and finally in the last row we are going to pick up the city number 3. From 3 to 0 we have the distance as 300, then 3 to 1 the distance is 500, and from 3 to 2 the distance is 400, and 3 to 0 is 0, right? So you can see this is the desired you can say the state, the problem space, right? So this is how we can create a problem space here. Now what I'm going to do is I'm going to define a main function, and inside of this main function I'm going to just assign it, right? This problem space is inside of the main function like this, and now I'm just going to define. Alright, so this is the main function. Now what I'm going to do is I'm going to print the solution by creating a function which is the hill climbing function, which will perform the whole algorithm, right? Which will perform all the steps inside of this algorithm. And here I'm going to pass the problem space to the hill climbing function, right? And now what I'm going to do is I'm going to write that if the name is equal to the main function, right, we are just going to call the main function, right? So in this way we have created our main function, and we have created the problem space as TSP, which you can see here, and then we have created a hill climbing function which is here, and this hill climbing function is used to perform all the steps. So let's move on to our very first step, which is to generate a random solution. So let's discuss how we can generate a random solution. Now before generating the random solution, we first need to define the hill climbing function, right? So I'm going to quickly define the hill climbing function here, and this function is taking a argument which is the TSP, right? And here we are going to create a variable which is the current solution variable, and we know that in the first step we will have to first generate a random solution from this problem space, and we have to assign it as the current solution, right? So this is the first step. So now now we will have to generate a random solution. Now let's see how we can do that. First of all, I'm going to import a random library which is used to pick up the random cities. Now the idea is that if we want to pick up a random solution, what we will do is we will pick up some random cities from this problem space, right? So we will pick up them and we will add them to the random solution, right? So let's say we picked up the first city as 2, and then let's say 0, then 3, and then 1, right? So we will generate a random solution, and this is the random solution where we say that the salesman will first visit the city number 2, and then it will visit city number 0. So you can see that it cannot after visiting 0 it will visit 3, and then after visiting 3 it will visit 1, right? So the salesman will visit the cities in this order, and you can see, you can calculate the route length in this case, right? So for this specific case, what will be the route length? From 2 to 0 we have 500 as the route length, right? Plus 0 to 3 is 300, so 500 plus 300, and then from 3 to 1 is also 500, right? One more thing is that I forgot to mention here that there are actually 3 steps or 3 constraints, not 2. The third one is that the salesman, if the salesman starts from the, let's say, city number 0, he will have to visit all the cities, and every city will be visited once, but the salesman will have to return to the same city from which he left, right? So the salesman, I'm going to just write the third step here, right? So is that the salesman will have to reach the city from where the salesman has started, right? So from here you can see the salesman started from 2, and then from 2 he went to the city number 0. The route length is 500. From 0 to 3 is 300, then from 3 to 1 is 500, and then the salesman will have to visit the city number 2. So from 1 to 2 the distance is 300, right? So what will be the final route length? You can see 500 is 1000, so it will be 1600 is the route length in this random solution, right? So we will generate a random solution. So let's see how we can write a function which is the random solution function. So in our Python code it will be the random solution function, and we are going to use the random library to generate a random number, and we will let's see how we can do this in Python, right? So this is the program, and here you can see we were at this line. Now here what we want to do is we want to write the code for the random solution. So what I'm going to do is I'm going to first create a list of cities, right? So I'm going to use the list function to create a list of cities that we have in our which is the problem space, and we're going to use the method range length tsp, which is the problem space, and this will generate a list of all the cities that we have in our problem space, right? So you can see in this we have the range function and we have length of tsp, right? So length of tsp will give us 4, and range is going to be from 0 to 4, right? So here the range will be, right? So in this step 1 we are creating a cities list, which is nothing but a list of all the cities that we have, and we are using the length of tsp, right? So the length function of the problem space will give us the value 4, and if we pass range 4, it is going to give us a range of all the numbers from 0 to 4 but excluding 4, right? So it is going to give us 0, 1, 2 and 3, and then we are going to use the list function to make sure that the range of all these numbers are pushed inside of the list, right? So now we have all the cities. Now we are going to generate the random solution here, right? So let's say we have I will create a list which will be an empty list initially, and this function is going to return this solution, right? But you can see we have not pushed anything in the solution. So let's push the random cities inside of the solution. For that I'm going to use a for loop for I in range length of tsp, right? So it is going to do the iteration from the length of tsp is 4, so the number is 0, 1, 2 and 3, right? So the values of I will be 0, 1, 2 and 3, and inside of this for loop what I wish to do is here I want to push the I will pick up a random city first, right? So I will create a variable random city, and inside this variable, which is the random city, I am going to use the cities which is the list of all the cities 0, 1 and 1, 2 and 3, and inside this I have to pick up a particular city, right, which will be a random city. Now how we can do that is we can use the random dot randint function, which picks up a random integer, and we will have to provide it the list of all the integers from where we want to pick up the random number, right? So the list will go from 0 to the length of cities minus 1, right? So the length of cities is 4 and 4 minus 1 is 3, so it will generate a random number from 0 to 3, so it can be 0, 1, 2 or 3, right? So let's say after this step in this for loop it has generated a random city, let's say 2, and now what we want to do is inside of the solution we are going to append, right? So solution dot append function is there inside of a list, and here we are going to append the random city to the solution, right, which is the random solution. Alright, so here also there should be a square bracket. Now what I want to do is, since we have pushed a random city, which is let's say 2 is the random city, now I don't want that in the next iteration it may happen that the random integer will pick up integer which can be 0 to 3, right? So it can be 0, 1, 2 and 3. So what I want is, if you have pushed a city inside of the solution, do not push it again, right? So what I can do is I can use the cities dot remove function to remove the random city, which is basically a number from 0 to 3, right? If we have appended it in the solution, we will remove it from the cities, so that in the next iteration of this for loop the solution will not append a city which has already been appended, right? And then finally we know that it is going to return the solution, right? So this is how we are going to write our random solution part. Alright, so now let's test this part, right? What I'm going to do is here inside of the hill climbing algorithm I am just going to print the solution, right? So let's print the current solution to see how it is working, whether it is picking up a solution or not. So I'm just going to write the changes here, and let's open up the terminal, right? So the changes are saved. Here now I am going to run the python 3 tsp solution dot py. Alright, so it says invalid syntax solution, so I think maybe there is some problem in here. Alright, so you can see here this is the random solution part, and here it is showing us the mistake at this line, right? So solution equals to this is not valid. Let's see what is the problem here. So you can see here there should be one more circular bracket, right? Right, so in the cities we have to write, okay, so one more circular bracket should be here, we will have to close the list also. So just writing the changes, and let's just run it again. Alright, so you can see that it shows that there is some, okay, so there is also a mistake here. Alright, so again we will have to make sure that it is, we will have to correct it. So here in the random city function, you can see we have a closing bracket here, and this random integer function is not closed, right? So we will have to close it. Here I am closing it, and again I'm going to write the changes, and let's run this again. So now you can see that it has picked up this as a random solution, right? So it is displaying a random solution 1 2 3 0, and every time you run this program it is going to pick up a random solution. So you can check by running this again, right? So now you can see it is again generating a random solution of cities, right? So this is our first step, where we actually define the first part of the algorithm is to generate a random solution. Now one important thing is that once we have generated a random solution, right, here we have the random solution, and let's say the cities that it has picked is 2 0 3 and 1. Now important thing is that this is not the solution, right? It is just a random it is a collection of random cities. The solution will be the root length of this whole space, right, of all these random cities. So the traveling salesman will travel from the second city, then 0, then 3, then 1, and we have already calculated that the route length, if the salesman is going to follow this route, these cities in order, the route length will be 1600, right? So the random solution is 1600, which we have generated. So we actually need a function which will generate a random route length, right? Route length of the solution. We want to generate the route length of this whole solution, because that is the main part of the algorithm. We want to find out the shortest path, right? So in the next step, we let's assign this as the step B part of this step A, right? This one was the A part. In the B part, we want to find out the route length of the solution, right? So let's see how we can do this here. Now here you can see we have the hill climbing algorithm, and what I'm going to do is I'm going to remove this line, and here I'm going to create another function. So at this place we will have to find out the route length of this random city. So I'm going to assign it as current route length, right, is equals to, we are going to call a function route length which calculates the route length of the given, we will give it the problem space, right, to because in the problem space we have all the route lengths, and then we are going to pass the solution or the current solution like this, right? So you can see I have created a variable current route length which will hold the value 1600 was in our case. So it will calculate the route length for the current solution. We will pass the TSP, which is the problem space, which has all the data of the routes of every cities, and we have the current solution also, right? We are passing the current solution to this function route length. So let's define this function route length here, and here we have two arguments, TSP and the solution itself, right? So inside of this function, let's do some, we are going to perform some steps here. right? In the root length, first we will assign the root length as 0, and then what I am going to do simply is I am going to create a for loop which will go from I in range, again the length of the solution, right? So we will go from one city to the another. So I will hold the value 0, 1, 2 and 3, and what we are going to do is we are going to assign, right, we will have to keep adding the root length, so plus equals to, and here we want the root length, right? For that we will have to use the TSP list, and inside of the TSP list we are going to pass two arguments, one which represents the row and the second one represents the column. In the first one I am going to pass solution I minus 1, and in the second I am going to pass solution I, right? So we are what we are going doing is, in this line I'm just going to show you here that in the root length part we are actually using root length plus equals TSP, which is our problem space, and inside of this TSP we are going to use the row and column, right? So I, the solution of I minus 1. So here I have the solution, we will start from I minus 1, and then in the second argument I am going to pass solution of I, right? So what we are doing is we are appending the root of each and every city. So you can see in the solution, first of all the I will have value 0, 1, 2 and 3. So if we pick up 0 in the first iteration, the value of I is 0, so you can see the value at the 0 position is 2, right, in the solution index, right? So solution of I minus 1, right? So I is 0, so I minus 0 minus 1 will be minus 1. So solution of minus 1, if you will try it inside of the Python, you will know that solution of minus 1 will basically give me the last number, right, which is 1, right? So solution of minus 2 will give me 3, right? So it goes from the last order if we have negative inside of the index, right? So solution of minus 1 will give me 1 here, right? So in the first iteration I have TSP, solution of I minus 1 is 1, and in the second part we have solution of I is equals to 0, right? You can see 1, 0 is the answer that we are getting. So what is the value of TSP 1, 0? You can see from 1 to 0 I have the distance 400, right? So the reason why we are starting from I minus 1 is because the salesman will have to also reach from the city from where it started, right? So I minus 1 is will give me minus 1 in the first iteration itself, right? So it will calculate the distance of 2 and 1 also, because the last element is 1, you can see, and basically solution of I minus 1. Alright, so TSP of 1, 0 you can see is going to be 400. So we are going to append it in the root length. Initially it was 0, now it will become 400, and then the value of I will be incremented to 1. 1 minus 1 will be 0. So here we have TSP of 0, and then we have solution of I is equals to 1, so 0, 1, right? So 0, 1 is 400, right? So you can see from the first two iteration itself we are actually getting to this value twice, right? This root length is calculated twice, 1, 0 and 0, 1, and this will happen in all the cases, but it does not matter what your random solution is. It will start from I minus 1 and I, so it will generate 1, 0 and then 0, 1, and you can see we are actually appending the root length of 1 0 and 0 1 twice, right? So the reason why we are doing it twice is, you can see that from this example itself we will have to add the 500, and because we started from whatever node we started, we will have to reach it again here, right? So we will have to you can say let's say this is the solution 2031. so the salesman started from 2, right, and then from 2 to 0, right? 2 to 0 is 500, so it is going to append that value, and then from 0 to 3 is going to be here, and then 3 to 1 is here, and you can see the last step or the last root remaining is the root between the first and the last element of the solution, right? So you can see the first and the last element are 2 and 1, so this should not be TSP 1 0. I made a mistake here. Solution of I minus 1 is actually minus 1, and solution of I minus 1 is minus 1. So alright, so it should be 1, so it was correct. And now here we have solution of I, the value of I is 0, so solution of 0, right? Here I made a small mistake here. So solution of 0 is not 0. You can see at the 0th index I have the value 2, right? So it should be TSP 1 2, right? So the row is 1 and the column is 2, and from 1 to 2 I have the distance as 300. In the next iteration I will have the value 2 1, right? And this is also 300, right? So this is the reason, this is the main reason why I am writing solution of I minus 1 and solution of I, so that we can cover these two distances. This is a very important part, and if you will test this out, you will get to know how this root length is calculated. Now returning to our program, here we have successfully calculated the root of this the root length of this solution, and now we are simply just going to return the root length of this function, right? Now here you can see this is the current root length, so let's just test out whether the root length we are getting is correct or not, just checking whether the function root length is working correct or not, right? So I'm just going to write changes here, and let's run this program again. Okay, so it says syntax error, return root length. All right, there is some problem in this code here, right? In return root length. All right, so again I made a mistake here. There should be one more square bracket here, right? Now it's fine. So again I'm going to write the changes and run this program, and now you can see it is displaying the root length as 1600, right? So I want to also display the solution, and then we will understand it much better. So here I'm going to print one more thing, which is the solution, right? So print the current solution also, so that we can verify that the root length is calculated correctly. Again write changes, and again I'm going to run this. So you can see that it shows the random solution as 1023 and the root length is 1800. You can calculate that, it will evaluate as this, right? So this is our first step where we have generated a random solution which is 1800, right? So if you take a look at the algorithm, we have generated a current solution as 1800. Now what I want to do is I want to find out the neighbors of this solution, right? All the neighbors of this solution. So in the second step I want to get the neighbors of this solution, right? Now the question is, how can I get the neighbors of this problem? In this problem, how can I get the neighbor of this solution, right? So you can see that in this solution, what we can do is we can swap the cities, and basically neighbors means that the value, the route length should be similar to you can say it should be similar to the other solutions as well, right? It should match it. It should have a value which is you can say near about 1800. Now how I can do that? You can see the solution is 2, 0, 3, 1. What I can do is I can just create neighbors of this solution by swapping some cities here. So let's say I swap 2, 0, so I can get another solution which is near about this solution, right? It will give me a value. So this is a strategy that we are going to use in step number 2 to get the neighbors. Now let's say in the same solution I swap, instead of 2, 0, I'm swapping 0, 3, right? So it will be 2, 3, 0, 1. Then I will swap 3 and 1, so we will get 2, 0, 1, 3, right? So in this manner we can generate the neighbors. For all these neighbors we are also going to calculate the route length, right? For all of these we will get the route length here, and then out of all these route length we are going to pick up the best one, because that's the main objective of the steepest ascent hill climbing algorithm. We will pick up the best one and we are going to just iterate over these steps, right? Or we are going to just loop over these steps again and again, which is to get the neighbors, find their route lengths, pick up the best one, and we are going to assign the best one as the current solution. We know that, right? So let's see how we can write the function of get neighbors inside of our Python program. And here what I am going to do is I will create another variable which will be the neighbors variable, and it will hold the value of all the neighbors that we are going to assign, right? So there will be a get neighbors function, and this function will get all the neighbors of the current solution, right? So we will have to pass the current solution to this function get neighbors. Alright, so let's define the current the get neighbors function. So we will define it at this place, right? So here I'm going to write define get neighbors function. We have the solution here, so we are going to pass the current solution, which will be here like this. Now what I'm going to do is in the get neighbors function I will create a simple list of all the neighbors, right? All the neighbors, and initially it will be empty, right? Now what I want to do is I want to create all the neighbors, right? So for that I will have to use a for loop which goes from for I in range. Again it will be same as the length of the solution, and inside of this there is another trick, which is we are going to use another loop which will go from j position, right, in range I plus 1, and I will explain why we are using these two different for loops, which is the nested for loops. The second parameter will be the length of the solution, and here we are going to first create a copy of the solution, right? So whatever solution we have, I'm just going to create a copy of that solution, and we will copy it inside of neighbor. Alright, so to swap the cities we are going to write a simple formula, which is neighbor of ith position will be equal to the solution of jth position, right? So basically why we are using two nested loops is that the first loop, which is for I in range this one, right, which you can see here, this for loop is used to actually navigate to all the cities in the solution, right? So if you can see here we have the solution as 2031, right? 2031. So what the first for loop will do, it will pick up the value of I and it will fix it to a particular position, right? So let's say initially the value of I is 0. Now what we will do is we will start another loop which will go from j plus 1 position, right? And it will navigate, or you can say it will iterate over all the elements remaining. That's why we are choosing I plus 1th position, right? So this j loop will go from I plus 1th position till the end, which is the length of the solution, and that is what we are going to do. We are going to pick up every jth element and we are going to swap it with the value of I, right? So the neighbors of I position gets swapped with the solution of jth position, right? And j position is actually starting from I plus 1 till the end of the solution. So here you can see this at this place we are actually doing the swapping work. So the neighbor of ith position will be equal to the solution of jth position, and in order to perform a perfect swap we will also have to make sure that the jth position of this neighbor, right, which is actually the rest of the elements, will be equal to the solution of ith element, right? And now finally what I am going to do is I am going to append this neighbors, right? I am going to append the neighbor inside of this neighbors, right? And finally, since this function will return the list of all the neighbors, right, we are going to return neighbors here, and you can see that this is how this function works. It will just create a copy of the solution. The two loops are to fix a particular number and swap it with the other cities, right, one by one, and we are once we have done the swapping work, after each and every swap we are going to append the neighbor inside of the neighbor solution, which will be the final solution, right? So from here you can see when we are at when I is equals to 2, j will be I plus 1, which is 0. So we will swap the values of 2 and 0, right? So it will be 0, 2, 3, 1. So after swapping we are going to push it inside of our neighbors. This is actually the neighbors list, so we are going to swap it here, right? So here we are doing the swapping work and it will go on until the end, and it will pick up every element, right? So it is going to push all the neighbors one by one by swapping. After every swap, remember that once we have done the swapping work we will append it as a solution to the neighbors, right? So in this way we can get all the neighbors. Now what I'm going to do here is I am going to just print all the neighbors so that we can test whether this is working fine or not, right? So here I am going to actually do the print of all the neighbors to just see whether this is working correctly or not. And one more thing is that we also need to print the solution, so that we print the current solution so that we can compare whether the neighbors that it is picking is actually the neighbors of the current solution, right? So it is the current solution like this. Alright, so I'm going to just save the changes here, and then I'm just going to run the Python program, python 3 tsp solution.py. Alright, so we have some error here, print current solution. Let's take a look at this. Alright, so here I made a mistake. Again, there should be a circular bracket. Right, here you can see the spelling mistake I have done. It should be h, right? Neighbors, and again saving changes, running the program. So now you can see here Now it is working fine. Let me do that again. So the solution, random solution it generated is 1 2 3 0, right? So in the first iteration it picked up the first element and it swapped with the jth element, which is actually running from I plus 1 till the end. So you can see 1 is swapped with 2, right? So 2 1 3 0 is our first neighbor, and then you can see it will increment the value of j. Now j is pointing to 3 and I is pointing to 1, so 1 and 3 gets swapped, right? So you can see the solution will be 3 2 1 0, right? And in this part we will swap 0 with 1, so it will become 0 2 3 1. In the next iteration of the ith part, now I will get incremented to 2 and j will be j plus 1 to n, right? So now 2 will get swapped with 3 and then with 0. So you can see when 2 get swapped with 3, it becomes 1 3 2 0 and 1 0 3 2, and similarly we have these neighbors, right? So now what we have done is we have done 3 crucial steps of this whole algorithm. First, we have generated the current solution, we have generated the path, and now we have generated all the neighbors. Now what we need to do is we want to write a function which will basically it will find out the root of all of these neighbors, right? So we have the algorithm to find the root of a particular solution, so we will find out the root length of all these possible neighbors, and out of all that we will pick up the one which is the best, right? The best one will get chosen, and then we are going to make sure we create a loop to basically finish this up, right? So that we can get up to the shortest path, the shortest route. So I've already written the program here, right? And I will show you what are these are the functions that we have already written, right? The next function that we are going to write is the best neighbor and the best route length, which you can see in this line, right? So in this line we have created two variables, best neighbor and best neighbor route length, and then we will get the best neighbor, right? There is a function get best neighbor which will get the best neighbor out of all the neighbors by comparing it with the TSP elements, right? Because the TSP, which is the problem space, it contains all the route lengths. Now you can see the get neighbors function is very easy here, right? We create the route length, right? We get the best route length equals to route length of TSP and neighbor 0, right? So we pick up the route length of the 0th neighbor, right? In the neighbors tag, we can see in the neighbors list we have different solutions. So the 0th solution, and we will pick up the route length for that, and then we are going to assign that neighbor as the best neighbor, and we are going to iterate in all the neighbors, and we will get the current route length, right? You can see in this line we are getting current route length equals to route length TSP neighbor, right? So we will get the current route length, and if the route length that we are getting inside of the neighbor is less than the best route length, and remember that the best route length is in this line, right, which is actually initially the route length of the 0th neighbor, and we will compare it with the current route length, which is actually enabled by this for loop here, for neighbor in neighbors. And it is very simple task. If you will read this function, it is very simple. The most important functions were the get neighbors, the route length, and the random solution functions, and to get the best neighbor we are just going to use these. Right now here you can see when the current route length is less than best route length, it means that we have found a neighbor which is better, and then what we are going to do is we are going to assign the best route length and the best neighbor as the neighbor and current route length, and we will keep on going on updating this with by comparing all the neighbors, and at last we will be able to get the best neighbor and the best route length, right? So this function was simple, that's why I am not going to waste time on writing this function. You can see this, it's very simple. Just by comparison and running a for loop, we can find out the best neighbor and the best root length. Now you can see that this function get best neighbors will return the best neighbor and the best neighbor root length. Now we have ended with the first three crucial steps, and the fourth step is to find the best neighbor. Once we have found out what is the best neighbor, what we are going to do is we are going to run in a loop, right? So you can see here inside of our while loop, which is our step 4, we have best neighbor root length is less than current root length, right? So let's say we have found that the neighbor is basically, if you take a look at this diagram, right? So let's say this neighbor turns out to be the best neighbor out of all these neighbors. Now what we are going to do is we are going to compare the root length, because that's the heuristic value, right? So it's important that I write here that the heuristic in our case is the root length, right? And current root length is 1800. We are going to compare that this root length is less than the best root length, right? And then only we are allowed to proceed, right, inside of a loop. That is an important point. So if we want to go inside of a loop, we will have to compare that the current root length is not better than the best root length, right? And then what we are going to do is now if this is the best root, we are going to assign this one as the current solution, right? That's what we do in the steepest ascent. We find out the best neighbor and we assign the current root length, right? So here in this function, this while loop, you can see we have assigned the current solution as the best neighbor, and we have also assigned the root length as the best neighbor root length. Now at this point we want to find out, we are again going to do the same thing. We are going to find the neighbors from the current solution. Remember that the current solution has been updated, right? Now it is pointing at the best one, right? Now at this step we will have to repeat the step, which is we want to find out the neighbors of these this current solution, and then again we will pick up the best one, right? So here you can see we are actually trying to pick up the neighbors of the current solution, which is now the best solution logically, and then we will again find out the best neighbor and the best neighbor root length, right? So we are going to update the current solution to the best neighbor, and at the end of this loop, at the end of this while loop, we will get to the best neighbor and the current solution will point to that, and the loop will end because no longer we are finding any neighbor root length which is better than the current root length. At this point this while loop will break and will exit, and we are going to return the current solution, right, which is going to be the solution which the salesman is going to follow, and we will also display the current root length. So this is the basically the fourth step, is it goes from here, right? So it's very easy to understand at this point. The three important functions were the random solution function, the root length, and the get neighbors, right? This was the basic crux of this whole algorithm, and these steps were relatively very easy, right? And now what I'm going to do here is I'm going to just make sure I'm going to show you the solution of this program. Okay, so it should be tsp.py, right? So now you can see here this was actually to display the neighbors, right? The solution, the final solution is here in this line, which is 3012, and the root length is 1400. So this is the shortest path and 3012 is the solution. One important thing is that if I will rerun this program, you can see that the solution is changing now. You can see the solution has changed to 0, 1, 2, 3, but the root length remains the same. It is still 1400, which is the shortest path, and logically you can even check this. you can see that this is a rectangle 400 by 300. So obviously the shortest path is not to traverse the diagonals, right? So if we will not traverse the diagonals, it will be 400 plus 300 plus 400 plus 300, which equals to 1400, which is the shortest path. And no matter what path you are following, you can follow 21032 or 23012, right? It does not matter. So you can see that's why the solution of the current solution is changing, but the route length remains the same. If you will run this program again, you can see there is a difference, and it will always show a difference. Now you can see that in this particular example, we actually have a global optimum, right? We do not have any local optimum. If we try to expand this traveling salesman problem in such a manner that we obtain some local optimum also, right? In that case, this algorithm may fail. That is the actual you can say the limitation of the steepest ascent hill climbing algorithm. So hope you have understood this algorithm, this implementation. Make sure to also do it yourself, so that you will be able to understand each and every step. And if you are facing any problems, you can just go to the different steps. I have given the timestamps of all the steps inside of this video, so you can check that out also. So that's all for this tutorial. If you have liked this tutorial and my efforts, please make sure to subscribe my channel and also share this video with others, so that I will get a better reach. And basically that's all for this tutorial. Thanks for watching.